All right, 4.4, we started this section last time called the dot product. Let me remind you of where we left off. The dot product is actually one of two products for vectors. It's the easier of the two. The one that we will not work with in this class is called the cross product. For the dot product, what we do is we take each of the components of the i's and we multiply them. We take each of the components or the coefficients of the j's and we multiply them and we add those two values together. And when we do that, we end up with a scalar. We get a number. So this actually results in a number. Okay, and we'll talk about some of the things that this tells us as we get further along. We actually just did a few examples last time. So when we were doing these, we first did this one and we found out that when we did u dot v and we did v dot u, we got the same thing. And that's a property that's called commutative, and we'll actually have a slide that's going to show that as the commutative property later. But we actually saw one and saw how it worked, and it made sense because multiplication is commutative and addition is commutative, so it seems to make sense to us that we should be able to do a dot product because it only involves the multiplication and addition, and it also be commutative. Then we looked at scalars. So if we multiply a scalar, the number 4, by one of our vectors, and then we do the dot product after that, we saw that we got the exact same thing as if we did the dot product first and then multiplied the scalar second. And that's kind of an associative kind of property that's going on there. And we saw an example of that one working out for us. And then the last one that we did was this one, number 3. And we did two dot products and we added them together. But we sort of made an awareness of the fact that when we did this dot product on number 3, the way it was originally stated, that there was a v dotted, if you will, with each of the two pieces, and then they were added together. And if we think about what we do with multiplication in general, and we say we can pull something out, or FOIL, or factor, or undistribute, those kinds of phrases, we kind of use the same way, we can do that here as well. And so if we pulled that vector v out, added the two vectors together first, we got the same thing. And that's a distributive property at place. And that leads into our next slide. We have several properties listed here. They're not all of them, but they're the ones that are mentioned primarily in your book, so they're the ones I put up here as well. The properties of the dot product. Commutative. That was what we saw in example number 1. It doesn't matter whether I do u dot v or v dot u, I will get the same scalar quantity. Distributive. When I have u dotted with v plus w, that's the same thing as u dot v plus u dot w. And those vectors on that second one should all be in bold, and they didn't get them all in bold. I apologize, but they should all be bolded just like the one before. Magnitude. Magnitude is actually the same as a dot product. Now, we looked at magnitude before. I'm going to write this at the bottom to remind you. Magnitude of v is actually taking the square root of a squared plus b squared, right? That's what we defined it as before. So I'd like for you to consider if we had this vector, this is the one I'm referencing, ai plus bj, and we did the dot product with itself. So if I did the dot product of v with itself, that would mean I would do a times a plus b times b, correct? That's a squared plus b squared, isn't it? That's the same thing I'm getting, it just doesn't have a radical over it. Yeah? So what this actually shows at the end here is that this is the same thing as having the square root of a squared plus b squared, where it's been squared. So the magnitude is the same as the square of the dot, the square, magnitude squared is the same as the dot product of the vector with itself. And the last one, we actually talked about this in a previous section, not with dot products, but about how zero vectors work. If I take the vector 0 and I dot it with v in either direction, all that means is that I'm going to be multiplying 0 times a and 0 times b. Clearly that zeroes everything out and I get the zero vector. So this is the zero property or the zero vector property for dot products. There is an alternate version for dot products that sheds a little bit more light on what it is that dot products actually are able to find for us. Okay? That definition looks like this. So if we have vectors v and w, and we have an angle theta that is between them. So picture-wise, let me just draw a sketch here. You've got a vector v, you've got a vector w, there's a angle theta between them. Everybody good so far? Okay. Well, then the dot product is actually the same as the magnitude of v times the magnitude of w times the cosine of theta. In other words, I can use the dot product to find an angle between two vectors. Okay? So we've done all these dot products. They're pretty simple to do. Do a little bit of multiplication, a little bit of addition, we get a value. That would find the left-hand side of this equation. We also know how to find magnitude. We did that in section 4.3. So we can find the magnitude of v and we can find the magnitude of w. So those three quantities are all arithmetic. Okay? I realize they're presented in a little bit of different ways, but it's all elementary kind of math stuff because it's just addition and multiplication things, okay? You got a little bit of a square root, I should say that. That's maybe not quite fair. You do have square roots with the magnitudes. But then cosine of theta is allowing us then to find the angle theta between them. So let's do an example. This one wants us to find the angle between v and w. We're going to round to the nearest tenth of a degree, which I put that in because that's what your book does, but I find it a little bit odd, I'll just be real honest with you, because everywhere else they've rounded to the nearest degree. So I don't know why now they decided they want a tenth of a degree, but just pay attention. I wanted to make sure my notes match that because I want you to pay attention that they might do that in your my math lab as well. So just make sure you're doing whatever they tell you to do with the rounding, okay? All right, so we have these two vectors that are given to us, and we have this formula on the previous slide. It says that the dot product of v and w is going to be equal to the magnitude of v times the magnitude of w times the cosine of theta. That's the formula. You can do this all in one formula. There's nothing wrong with that. I don't think there's anything that you couldn't handle with doing that. But there's also three distinctly different pieces that we've had formulas for. So I'm going to approach it where we do each of these three pieces, and I'll number them separately and then put them all together. So I'm going to call this piece 1, this is going to be 2, and this is going to be 3. I'm going to do those three pieces, and then I'm going to put them all back into this formula in its sort of bigger form, okay? If you want to do it all in the same formula, more power to you, that's fine. All right, so the first thing I'm going to do, number 1, is v dot w. That's what this section's been about. So what will I be multiplying when I do v dot w? What will this step look like? Somebody just tell me the numbers. Let's go.
-3 times 5 plus 4 times 12.
Okay, everybody good with that? -3 times 5 plus 4 times 12, and you're welcome to grab a calculator at that point, get me a number. So what will this give us? 33. Okay, everybody good with that? Okay, that's the first step. Step number 2 is to find the magnitude of v. Magnitude of v is the square root, and it's the components of v that are squared now. So I have -3 squared plus 4 squared. So what is -3 squared plus 4 squared? So just tell me the part that's underneath the radical first.
Square root of 25.
That'll be square root of 25, which has a lovely form. They don't always. This one did. It's 5. And the third piece is the magnitude of w, square root. And then I have 5 squared plus 12 squared. What is 5 squared plus 12 squared? Yeah, it's 169. Very good. This one's also a very nice radical. They're not always going to be. What's the square root of 169? It's 13. Okay, so these are the three pieces. And now I'm going to go back to this formula, and I'm going to put them in the right places. So this is going to be 33 on the left equals 5 times 12 cosine of theta. $513, sorry. Zooming in and zooming out. How about a 13 there? Okay, I think everything else is okay. Is that right? Okay, what am I going to do to figure out what theta is from this point?
Get cosine theta by itself.
I need to get cosine theta by itself, okay? So if you would like, somebody tell me what 5 times 13 is. Do you know? It's 65, yeah. So this is 33. I have 65 cosine of theta. And then just like Isaiah said, we want to get the cosine of theta alone, so we will divide by our 65. So we have the cosine of theta equals 33 over 65. What are we going to use our calculator for now that it's calculator time?
I need angle measurement to do cosine.
Okay, so what are we going to do with it, though, to do that? What do you want to do? Say it louder. You're right. You're right. You're right. We're going to do the inverse, right? We're going to do the inverse. Yeah, it's an inverse function. You guys all know it. That's why I want somebody to say it. Yeah, it's an inverse. So we're going to take the theta. It's going to be by itself now, and we're going to do the inverse right here. You guys need to have more faith in yourself sometimes. Just go for it. 33 over 65. We do need to be in degrees. We're working with degrees here. And it says we're rounding to the nearest tenth. That means 1 decimal. So if I take this, I don't even think I did that on my paper actually, which is fantastic. If I take this and I do the inverse cosine of 33 over 65, what do I get? Did anybody do it? Inverse cosine of 33 over 65. Is it 0.5? Rounded? So 59.5 degrees. Okay? It's almost 60 degrees. So in terms of this sort of picture of what we have going on, we found that angle that's between them, if we line them up with the corners at the same spot, right, is about a 60-degree angle between them. Make sense? Okay. So this kind of goes back to the things that we were doing. We did this back in, I can't remember if it's chapter 1 or chapter 2, where we're talking about like bearings, where people talk about, how many degrees north of east of this kind of stuff. Vectors are used in this way as well. All right, so this angle measure of how far the angles are apart and so forth would be along those lines of like trajectories of ships, submarines, those kind of things in the water. You've also got things in the air that would be doing that, right? So planes and such like that, okay? All right. There are 2 other things that we're going to take a look at in terms of our vectors. Parallel vectors and orthogonal vectors. Parallel vectors, you know what parallel means, right? So I keep doing this with my 8th grader, they're not 8th graders, 10th graders, excuse me, who are in geometry, and I keep going parallel. It's like this, right? Think railroad tracks. You think the lines on your paper, when you have lined paper, they're parallel. So if you have 2 vectors that are parallel, what that means is that the angle that is between them is either 0 degrees or it's 180 degrees. And I'd like to draw you the 2 pictures that that's describing because it sounds a little funny that there's 2 options. But right here, if this is 2 of our vectors, they don't have to be the same length, but there's just 2 of them, right? These would be parallel. You can look at this and agree with me. Yeah, these are parallel. The angle between them is 0 because remember what we do, in fact, I'll change my colors to show it better, is if you line them up with the corners at the same spot, there is no angle between them. They're exactly in the same position because remember, you can move vectors around wherever. It doesn't change the vector. Vector is just direction and magnitude. So if these are parallel, you could put them at the same starting point and they would lie right on top of each other. There'd be 0 degrees between them. Make sense? Now, the other option is that there's 180. So what would that look like? Well, it would look like one of them looking like this. And any idea what the other one would have to look like for this to work? Yeah, it'd have to go in the opposite direction like this. And if I lined them up end to end like that, then this angle right here would be 180 degrees. Okay? So what does it take to decide if vectors are parallel? Well, vectors are parallel in a very much the same way that their angle measures the same, right? That angle that we're looking at, theta, is the same, or it's 180 degrees opposite. But what happens is they're really just scalar multiples of each other, okay? They may not be the same length, but they're in the same direction. So this is just a multiple k times your vector that gives you the other vector. Now that k value could be positive or negative, right? Positive or negative. And it can be decimals, it can be fractions. It doesn't matter what its value is. It could even be the number 1. That would mean they're the exact same vector. That'd be okay too. But it would definitionally still be something that would be parallel. Okay, so a scalar multiple tells you that you have a vector that is parallel to another vector. So when you're looking at a problem like this and you're asked to find if in fact the vectors are parallel, what you're trying to decide is if there is some number that you can multiply one of them by to get the other one. And it's usually a pretty straightforward kind of thing. It's not going to be super complicated to look at and decide. But if you are not sure, and you're thinking, well, I'd like to know sort of like concretely exactly what am I looking for? Well, you're looking for this number and this number to have some number that is between them, like this, that makes it work. Okay, so what would it be for this one? It's a 2. This k value is 2. If that's the right number, if they're parallel, I should say, right? If they're parallel, what will happen is that same number will work for the 5 and the 10. Does it work? It does. Now, I don't need to you don't need to show me this, right? You don't have to write it out this way. But this is what you're looking for. Okay? This one's a really nice one. The number 2 works really nicely. If the number were a decimal, like let's say it was multiplying by 1.2, it might not be quite so obvious that you look at that and go, yeah, it's multiplied by 1.2, right? You might actually have to work a little bit more to figure out what those numbers are. But in general, the reason you're able to say this, is they're parallel, is that we can say that they're parallel because when k is equal to 2, which one do we have? 2 times v, is equal to w. Right? That's the number that we had. Right? This is our k. There is a k that works to do this. And if we had started with w and gone back to v, we could have done that too. Let me just make mention of that. You don't have to go from left to right or from smallest to largest. It will work okay if you go from w into v as well. So w had the number 6. And so if you did 6k is equal to 3, what would the k be if we were thinking about it from this perspective? Yeah, k would be 1/2. And that's okay too, right? Because it would still work. We would have 10 times 1/2 is equal to 5. It checks out. Our statement over here would look like 1/2 times w is equal to v. Okay, so you can go from smallest to largest or largest to smallest. It doesn't make any difference. If you don't like the idea of there being a fraction here, then just start with the smaller one, whichever one it is, and go from there. But negatives can show up here as well, right? I could have negatives involved. I could end up with a k value that's negative. There's nothing wrong with that. It is an option, and it would not change the fact that we could still have them parallel even if the k value were negative. Okay, all good? All right, our last piece in this section is what are called orthogonal vectors. Orthogonal means perpendicular, at least in the sense of what you're thinking about for this. So perpendicular is a word that we use to describe a certain relationship for lines. What would we say would happen if 2 lines were perpendicular? They would cross at a 90-degree angle, correct? We use the word orthogonal when we're talking about vectors that have that same property. Okay, slightly different vocabulary. We're dealing with a slightly different kind of object. Vectors and lines are not the same. Some similarities, but they're not the same. So 2 vectors are orthogonal if the angle between them is 90. Okay, everybody good so far? All right. The kicker to this is that if you have orthogonal vectors, their dot product is actually going to be 0. That's a really quick thing to check then, right? Now I want to show you why that works by the formula. Okay, so our formula said that the dot product is the same thing as the magnitude of v times the magnitude of w times the cosine of theta. Agreed? That was our formula for dot product with the angle part involved in it. Okay, so if these things, these vectors, really are 90-degree angles, right? So, or at a 90-degree angle, it would mean that we have a cosine of 90 degrees here. Everybody good so far? Okay, unit circle. What is the cosine of 90 degrees? It's 0. So what happens when this piece is 0 and it gets multiplied by the magnitudes of v and w? You still get 0. And lo and behold, there's that dot product all by himself on the left, and we've got a 0 on the right. We got 0. And this only happens when we're at the 90-degree angle. That's a little bit fuzzy. It would happen at 270 as well, but it'd be 90 degrees in the other direction, so we don't have to think about it as being different things. All right, are you guys with me? Because if we had a 270-degree angle, we'd get a 0 as well. But they'd still be orthogonal. It'd just be orthogonal in the sort of lower direction instead of the upward direction. It'd still be orthogonal. So if we want to determine if things are orthogonal, that's just another fancy way of saying figure out if the dot product is 0. That's all we have to do. All right, so let's figure out what the dot product is. So v dot w. So what will this look like if I write it out? 2 times negative 9 plus, good, negative 3 times negative 6. And what happens when we do both of these multiplications? Well, we get negative 18 and positive 18. So we do, in fact, get 0. So these are orthogonal. And let's just show, because we have a minute anyway, we got lots of minutes, but we're just going to show that that makes sense from the picture. There's nothing about this that's difficult for us to draw. We can definitely draw this picture. Okay, so we're going to do it. In fact, I'm going to switch my slide and we're going to use a grid because we can. Okay, so we have our xy ordered xy coordinate plane. Our vector v said that we are going to have, what was it? 2i minus 3j. So 2i means I'm over 2 here, and 3j means I'm down here. So this is my ordered pair that I would be landing at, and this is the vector v. Okay, everybody okay with that? So far, so good? Okay, the other vector, vector w, was negative 9i. I might have to change my scale for this to work, and minus 6j. So negative 9i, move this over here so I have more space, means I need to go to the left 9, correct? Let's see if I did enough. 1, 2, 3, 4, 5, whoops, 5, 6, 7, 8, 9 I did. And then down 6, barely, over here. I think this puts me right here. And the vector would look like, wow, that didn't work at all. Let's try again. That's not bad. This. Now, proof by picture is a terrible thing to do. General statement. Okay, y'all know that from geometry, right? Somebody told you somewhere along the way, just because the two sides look the same doesn't mean they really are. That's not what I'm trying to do here. What I'm trying to do here is look at this and say, does it seem reasonable? Does it look reasonable that this right here is a 90-degree angle? It looks reasonable. It's a good quick check step, especially if you're just doing a little quick sketch, right? Even if you don't have the scale quite perfect, you don't have a grid that you're doing it on, that's fine. If this picture had looked like this is my second vector instead of this one over here, right? If this one over here had not been here and we had this and we thought that it was orthogonal, this should give us pause to say, wait a minute, something's not right. Either I did some arithmetic wrong when I found the dot product, or either I drew it wrong. Let's take a minute and just see which one it is and fix it. All right, you with me on that? Okay, so this is one good quick check step to make sure something seems reasonable.